Welcome to The Explainer. I'm your host, and today we're exploring a topic that honestly sounds like it was ripped straight out of a sci-fi thriller, but it is deeply rooted in modern particle physics. As a documentary writer, I spend a lot of time looking into fascinating concepts, but we're going to talk about what might just be the ultimate existential threat. We're talking about an ecological catastrophe so profound, it literally rewrites the laws of physics from the ground up. It's a phenomenon known as false vacuum decay. Okay, let's dive into this. It's a question that keeps cosmologists awake at night. Could our universe just spontaneously end? For decades, physicists have been rigorously investigating the bizarre possibility that our universe might not actually be in its final, most stable form. Instead, the quantum fields that make up the very fabric of our reality, well, they might currently exist in a temporary, metastable state. Basically, we need to investigate how and why our entire reality might just be a passing phase. To really grasp the stakes here, we need to listen to the late, brilliant physicist Sidney Coleman. He delivered what is perhaps the most ominous warning in all of modern physics. He said, and I quote, "Vacuum decay is the ultimate ecological catastrophe. After vacuum decay, not only is life as we know it impossible, so is chemistry as we know it." Think about the weight of that for a second. If the universe transitions to what physicists call a true vacuum, the effects would be absolute. We're talking about the complete cessation of existing fundamental forces or even the immediate gravitational collapse of the universe. Every galaxy, every star, all biological life, full destruction. So, to understand this threat, we have to look at the fundamental physics behind it. In quantum field theory, a vacuum isn't just empty space. It's a space with as little energy in it as possible, though it's still buzzing with quantum fields. A false vacuum is a hypothetical state that exists at a local minimum of energy. It's locally stable, meaning it can stick around for a very, very long time, but it's not completely stable. It's metastable. Imagine a ball resting in a little shallow valley halfway up a mountain. It's secure for now, right? But if it gets pushed by a massive burst of energy, or if it simply tunnels through the rock via quantum mechanics, well, that ball rolls all the way down the mountain to the absolute bottom. And this brilliantly illustrates the core contrast we're dealing with. On one hand, you have the true vacuum, which represents a global minimum of energy. It is completely stable. On the other hand, you have the false vacuum, just a local minimum, metastable, and highly capable of decaying. The crazy thing is, the universe we live in, the physical vacuum state that surrounds us every single day, might just be that temporary local minimum. If microscopic quantum fluctuations allow even a tiny region to transition into the true vacuum, the macroscopic consequences would be totally unstoppable as it spreads. Now, who are the prime suspects in this cosmic mystery? To find the trigger, we have to look at the standard model of particle physics. Specifically, the stability of our entire universe relies on a very delicate mathematical balance between two fundamental particles, the famous Higgs boson and the heaviest fermion, known as the top quark. Their precise masses literally dictate whether the vacuum of our universe is stable, metastable, or completely unstable. Which brings us to 2012. This was a massive historical turning point at the Large Hadron Collider. The Higgs boson was finally discovered, and its mass was measured at approximately 125.18 gigaelectron volts. Now, when physicists plotted that number against the mass of the top quark, this specific value did something incredible. It placed our physical reality squarely on the metastable side of the stable-metastable boundary. Almost overnight, the purely theoretical concept of a false vacuum suddenly became a highly probable description of our actual everyday universe. The absolute precision of these measurements is paramount to whether this theory survives. Fast forward to 2022, and a reanalysis of data from a 2016 run at the LHC yielded a slightly lower top quark mass of exactly 171.77 gigaelectron volts. While this new number is technically closer to the absolute vacuum stability line, the crucial detail is that it still sits firmly within the metastable zone. So the continuous refinement of our data isn't disproving this. It only further reinforces the claim that our physical electroweak vacuum is currently metastable. So, assuming we are in a false vacuum, what exactly is the modus operandi of our destruction? Well, the lower energy true vacuum would form through a process called bubble nucleation. First, you'd have a high-energy event or a spontaneous quantum tunneling event. This instantly triggers a tiny, microscopic bubble of the true vacuum to appear right inside our universe. If this little bubble reaches a certain critical size, the energy inside overpowers the surface tension of the bubble's walls, and boom, it begins to violently expand outward. And the impact of this expansion is just utterly terrifying. These bubble walls blast outward across the cosmos at nearly the speed of light. Anything they touch, we're talking elementary particles, entire planets, stars, the whole shebang, would immediately decay or instantly collapse into black holes. The space-time inside the bubble would be fundamentally entirely unrecognizable from the reality we currently inhabit. With consequences that catastrophic, it's totally natural to ask, are we going to accidentally do this ourselves? Can human-made particle accelerators trigger vacuum decay? Over the years, there's been a lot of public fear and media sensationalism suggesting that highly energetic collisions, like those we produce in the Large Hadron Collider, might create mini black holes and artificially trigger a vacuum decay event right here on Earth. Now, what's really interesting about this slide is how a quick look at the raw data completely puts those fears to rest. The Large Hadron Collider reaches energy levels of about 8 trillion electron volts. Sounds like a lot, right? But naturally occurring cosmic ray collisions have been observed at energies of 50 million trillion electron volts. To put that into perspective, nature is already producing collisions that are 6 million times more powerful than our current human technology. As researchers have rightly pointed out, if high-energy collisions could cause vacuum decay, the universe would have ended a long, long time ago from natural cosmic radiation just striking planetary surfaces. So those fears of human-made decay? Completely unfounded. So instead of looking at human technology, researchers are looking up at the sky for natural triggers. Theoretical models suggest that extreme gravitational bodies could act as nucleation seeds. We're talking about evaporating Schwarzschild black holes, or primordial black holes that were generated in the ultra-high-temperature thermal plasma of the early universe. The mere presence of these black holes could hypothetically catalyze the decay, drastically reducing the lifetime of our false vacuum. Let's move to and see how this builds, because if a natural trigger sets this cosmic thriller into motion, how would we actually perceive it? The chilling truth is, we absolutely wouldn't. According to a fascinating 2005 paper analyzing global catastrophic risks, we might vastly underestimate the chances of being destroyed by vacuum decay simply due to an observer selection effect. Because the bubble wall is approaching at essentially the speed of light, any information or light from the event would reach us at the exact precise instant we were destroyed. Put simply, we would never even see it coming. Okay, before the existential dread fully sets in, let's look at the math. Direct calculations within the standard model estimate that our current vacuum state will last for more than 10 to the power of 65 years, with a 95% confidence level. To put that completely mind-boggling number into perspective, that vastly eclipses the current 13.8 billion-year age of our universe. That's enough time to let us sleep soundly at night, for sure. So the crucial point is that while the math points to metastability, the time frame implies deep stability for our era. But the future outlook remains wide open. Physics is an ever-evolving field, unknown forces in higher dimensions, completely undiscovered particles, or the lingering mysteries of quantum gravity could rewrite these rules entirely. Actually, scratch that, they could shift the division lines of stability and metastability in ways we haven't even dreamed of yet. Which brings us to our final, provocative thought. Are we simply a temporary fluctuation in a metastable reality? It's a profound, almost dizzying idea. The study of false vacuum decay isn't really just about cosmic doom. It's an incredible testament to our ability to mathematically probe the very fabric of existence, stretching all the way from microscopic quantum fields to the grand macroscopic fate of the universe. It leaves us in awe of the bizarre, beautiful nature of reality, and I hope it leaves you wanting to learn more about the incredible mechanics of our universe. Thank you for joining me on this explainer, and keep questioning the cosmos.